So in this session, we talk about the general stability criteria. Now, to discuss the concept, let's look at two examples here. One is for a simple tank that we have considered in several cases as an example. We'll try to find the model for these two tanks and then try to see how stability can be analyzed using the models. Now, from the conceptual understanding of the process, you can see that if you make a change in this inlet flow, so whatever was the inlet flow here, if we just increase it in a step manner, what happens is that the level start to go up, and when the level start to go up, also like this, outlet flow start to go up. So understand from the physical configuration of the process and from the first principles that when the level goes up, the outlet flow also goes up, and at some point this outlet flow will become equal to the inlet flow, and at that point the level become also steady. So these are the process what is called this open loop stable process. Now, if we develop the model of the process, we know that from the first principles, we can simply figure out that the accumulation term simply Fi minus Fo. Now, for this case, if we make the simple assumption that Fo, because if the level increases, the outlet flow increases. So, if in the deviational form we take the Fo, so initially if the level is here, if the level goes up, the outlet flow is here, so outlet flow will go also up. So we'll have F naught or Fo proportional to, say for the time being, let's assume it's directly proportional to Ht. Now that to be correct, it should be square root of Ht. However, after linearization, you see that it can be written as Fo proportional to Ht. Okay. So then we can write Fo some constant time Ht. Now if we plug in this value here, we'll get a dHt over dt plus Cht equals Fi, and if I write it as Fit. Okay, and if we then convert it into deviational form, we'll get this formulation in the deviational form. I'm not going into the detail of this. We have done it, and I assume we can do it. So we'll have then in the Laplace domain H prime s over Fi prime s will be 1 over As plus C. So I'll write it in this notation of what is called this pole zero form to make this constant to be 1. So I'll divide everything by A, and if I write it 1 over A equals B, I can write simply B over S plus another constant A, where A equals C over capital A. And I'll again write it as B over S minus A. We'll see why is this form important for this case. Okay. Now if we look at this transfer function and try to find out the response of this level due to a step change in Fis, we'll have H prime S B over S plus A 1 over S. Okay. I don't know that for this case, that if we take the inverse Laplace, H prime t will be b over a 1 minus e to the power negative a t. That's the inverse Laplace transform. We can do this math. We have done it for several cases. Okay. Now from here you can see that when the t goes to infinity, this term becomes 0 and this value becomes simply b over a. And when t is 0, this term is 0, this term is 1, so the entire term becomes 0. So it goes from 0 to b over a. Okay. So that's something. If we start from here, 0 in the divisional form, the final value will be something like b over a, and which is bounded. So we call this process that it has a bounded output. Okay. Now look at this process here. Now from the physical configuration of the process, we say that if there is a change, say initially it's maintained that this inlet flow equals with outlet flow, so the level is remained at the constant value. Now if there is a change in this inlet, say whatever manner step or other way, we'll consider the step input for this case. We say that the level will go up. So for this case, the level will start going up. So when the level goes up, this spring configuration, the float goes up, and that will cause this spring to go down and close the valve. Okay, so that can be just simple physical configuration that's designed in a way. Just if the float goes up, then the valve goes down, meaning the valve closes. So when the output start to go up, we see that this valve will, from there, will start to go down. And when this goes down, the level further increases because the outlet flow is now decreasing, the level further increases. So keep on increasing, and this keep on decreasing, and you see that okay, if the tank doesn't have a limit, the level will continue to go up and the outlet will continue to go down. Okay, so meaning this is what is called this unbounded. Okay, so you can call this to be unstable because the output is going to be unbounded. Now let's look at this from the model perspective. Again, we can have the same model structure. Minus FO. However, for this case, this FO is proportional to, so when one variable goes up and another variable goes down, the relation is not the inverse relation here for this case. Do remember that it's not the inverse relation, because in that case, if F1 equals 1 over H, in that case, if F1 increases, also H1 increases. So when one variable increases, another value decreases, the relation is simply negative H. So you can write it F naught to be equal to negative gamma H. Okay, and if you plug in this equation, we'll end up getting a dHT. So I write it in dt. We'll have negative gamma ht fit. So if we use the divisional form, we'll get the same equation, and the transfer function will be hs over fi prime will be minus gamma, which I can write as beta over s minus alpha, where beta equals 1 over a and alpha equals gamma over capital A. Okay. Now you see that the model equation can be represented as this one, beta over s minus alpha, in the pole 0 formulation. If there is a step change in the FIS, the H prime S will be beta over s minus alpha 1 over s And for this case, you will see that if we take the inverse Laplace, we'll simply get beta over minus alpha 1 minus e to the power minus alpha t. Just simply following the same notation we get here. So we'll get minus beta over alpha 1 minus e to the power alpha t. Now if we look at this response now, when t is 0, this is 1, so this entire term becomes 1. When t is infinity, this term really becomes infinity, so positive infinity. Okay, so that shows the response of ht because it's going to infinity. So this is what is called this unbounded. Okay, so this one was bounded, this one is unbounded. Now what is the relation between this and the transfer function then? Now if we look at this transfer function, we see here, I can write it as this beta over s minus alpha. This is the pole 0 formulation. So you see this, the pole here is, the pole is nothing but the solution of the denominator polynomial. So s becomes alpha. What we have seen here is gamma is a positive number, and that gives alpha also a positive number. And here the same thing, this c, that's a positive number, and that results in a to be also a positive number. So for this case, you see the pole is negative a, meaning it's a negative value, and here the pole is alpha, which is a positive value. Okay, so what this analysis shows you that to be bounded, this a is positive, meaning the pole is negative. And here for this case, this unbounded case, we see that this pole is positive because the pole was s equals alpha, pole is positive. Okay, so now we have seen this for one pole here. Okay, so we see that for this pole to be negative, it's bounded. For the pole to be positive, it's unbounded. Now the same thing you can see for a general transfer function. If we have ys over us is, say, if we write it the pole 0 formulation, the step response due to a step change in us can be expressed as ys will be, suppose a naught over s plus some constant a1 over s minus p1, another constant s minus p2. Now if you write it in the time domain, you will get yt a naught plus a1 e to the power p1t plus a2 e to the power p2t. Now if you see, if p1 equals, is p1 greater than 0, this term will be infinity. If p2 gets greater than 0, this term will be infinity. If p1 less than 0, this term will be bounded. P2 less than 0, this term will be bounded. So if either p1 or p2 is greater than 0, this yt will be unbounded. So you see that for this case, there is only one pole. If this pole is less than 0, it's bounded. If for this case also, this is only one pole. If pole is greater than 0, it was unbounded. If you have more than one pole, we see that if one pole is greater than 0, so it becomes unbounded. Okay, so that comes to the conclusion regarding what is the stability criteria. So the stability criteria simply is all poles should be negative. Okay. Now this is also not a full statement, because the poles also can be imaginary. Poles also can have imaginary part. And we know that for imaginary cases, always there will be one there. They comes in complex conjugate. So one part will have a positive imaginary part, another will have a negative imaginary part. So it should be that all poles should have negative real parts. So that's the criteria for stability. So the poles can be imaginary, the poles can be real, irrespective of whether they are real or imaginary. The real part should be positive for all the poles for a system to be stable.